Good day everyone, welcome to today's chemistry class, a continuation of the kinetic theory of matter. Today we'll be looking at the combined gas law, the Gay-Lussac's law, and the Avogadro's law. Don't forget, in the last class we talked about the Boyle's law, the Charles law, and the kinetic theory of gases. Now let's see what ideal gases means and what real gases means. Ideal gases behave as predicted by the kinetic molecular theory. Examples are the hydrogen gases and the helium gases. Now, gases are most ideal at high temperature and at low pressure, while real gases deviate from the ideal behavior, and the reason being that at low temperature, gas particles become attracted to each other. Now, under high pressure, gases occupy specific volume. Now, let's go to the next, which is the ideal gas law or the combined gas equation. This is gotten from the combination of the Boyle's law and the Charles law. If we recall from our Boyle's law, it combines volume and pressure, keeping temperature constant, while the Charles law is the relationship between the volume and temperature, where pressure is kept constant. And when we bring these two laws together, we have volume, temperature, and pressure all together equated to a constant. And when we know the arithmetic, we have P1 V1 over T1 equals P2 V2 over T2, depending on the number of variables you have. Now, quickly to the second one, we have the Gay-Lussac's law. Here, since Boyle's and Charles' law described physical behavior of gases, Gay-Lussac's looked at the chemical behavior, and his law states that when gases react, they do so in volumes which bear a simple ratio to one another and to the volumes of gaseous products, provided all gaseous volumes are measured at the same temperature and pressure. Now, one important thing here, we're talking about gases and volume. Now, this law is of great importance, but since he did not relate the gaseous reaction with the Dalton's atomic theory, this can be explained using the kinetic theory of matter. So we just used volume. For instance, a volume of hydrogen gas reacting with one volume of chlorine gas to give us two volumes of hydrochloric acid gas. Now the next one is the Avogadro's principle or law. Now, after the death of Gay-Lussac's, Amedeo Avogadro recognized the significance of this law. Now, he hypothesized that equal volume of different gases at the same temperature and pressure contain equal number of particles, and that number of particles are the moles. So he brought his own relationship in terms of moles. For instance, the equation here, we have one molecule of hydrogen plus one molecule of chlorine gas to give us two molecules of hydrochloride gas. And the Avogadro's constant or number is 6.02 times 10 to the power of 23, and this means the quantity of particles found in a mole. And at standard temperature and pressure, we have this Avogadro's number. That's the number of quantity of particles occupies 22.4 dm cube or liters. Now let's see general examples on Gauss' law. The first examples goes thus: we have a certain amount of gas occupy 200 cm3 at 1 times 10 to the power of 5 Newton per meter squared. We are supposed to calculate the volume when the pressure is 2 times 10 to the power of 5 Newton per meter squared at constant temperature. Here the data were given as the first volume, which is 200 degrees Celsius, 200 cm3, centimeter cube, and the first pressure, which is 1 times 10 to the power of 5 Newton per meter squared. Now we have to calculate the second volume, which is unknown, and the pressure is given as 2 times 10 to the power of 5 Newton per meter squared at constant temperature. Now Boyle's law has to do with constant temperature, so we're going to use that here, and this says P1 V1 equals P2 V2. Here we'll make V2 the subject of formula since it's the unknown. So V2 will be P1 V1 over P2, which will give us, on substitution, 1 times 10 raised to the power 5 times 200 divided by 2 times 10 raised to the power 5. And when we do the arithmetic, we're going to get 100 centimeter cube, and that's the volume. Now, the second question, those girls will have the volume of a given mass of gas measured at atmospheric pressure and 27 degrees Celsius is 3 dm cube. We have to calculate the volume of this gas at 127 degrees Celsius at same pressure. Now, here the data given is, we have the volume, first volume 3 dm cube, this first temperature 27 degrees Celsius. Now, since we're given the temperature in Celsius, we need to convert it to Kelvin. That's by adding 273 and we'll get 300 Kelvin. Now we need to calculate the second volume, which is V2, and the second temperature given as 127 degrees Celsius also need to be converted to Kelvin, which is 400 Kelvin. Now, Charles' law related volume to temperature, so we're going to use V1 over T1 equals V2 over T2. I'm making V2 subject of formula. We'll have V2 equals V1 T2 over T1, and V2 will give us 3 times 400 over 300, which equals 4 dm cube. Now, let's see further examples. Is on the Gauss law. We have a certain mass of gas occupies 330 cm cube at 27 degrees Celsius and 9 times 10 to the power 4 Newton per meter squared. Calculate its volume at standard temperature and pressure, and we're given the standard pressure to be 1 times 10 to the power 5 Newton per meter squared. Now, the data we're given here is the first volume, which is 330 cm cube, the first pressure 9 times 10 to the power 4 Newton per meter squared. The first temperature is 27 degrees Celsius, which is 300 degrees Kelvin. Now, we have to calculate the second volume at standard temperature and pressure. We're given the standard pressure to be 1 times 10 to the power 4 Newton per meter squared, while at standard temperature it's always 273 Kelvin. Now, since this question combines both pressure, volume, and temperature, we're going to use the combined gas equation, which is P1 V1 over T1 equals P2 V2 over T2. Now, on making V2 subject formula and substitution of the data given, we have 270.3 cm cube. Now, our homework for today, we have to state Boyle's law and Charles' law, give the mathematical representation of the combined gas law, then state the Avogadro's law. Thanks for viewing.